I am very excited to share my research with you, but first I want to spend a little bit more time digging into catalysis. We heard a great talk from Melissa that really introduced that concept and how important catalysts can be, but I do want to spend a little more time digging into that. First, I'm sure many of you are familiar with the high school definition of catalysts, right? And as we heard Melissa say when talking about enzymes, these are materials that can make reactions happen faster, or in some cases make reactions happen where they might not happen at all. And this is the progress of a reaction shown versus the energy required to make that reaction happen, right? So you can see that without a catalyst, there's a lot of energy required to push that reaction forward and get to your desired products. Whereas when you introduce a catalyst, now we've lowered that barrier quite a bit. This is really important. Again, as we heard, catalysts are in every product. Everything in this room was made, most likely, with a catalyst of some sort. They are everywhere. I love putting numbers on things, so that translates here to 90% of all products have used a catalyst at some point in that process, which equates to a $900 billion industry. And that's in fuels, that's in pretty much all commodity chemicals, pharmaceuticals, everything. My personal favorite example is ammonia, right? A very simple household cleaner, but the catalyst that was discovered to make ammonia through nitrogen gas was huge. That same process actually saved the entire world from starving to death, but also fueled the rise of Hitler and a world war. So highly recommend everyone read this book. It's one of my all-time favorites. It's about the first industrial example of a catalyst, and also the company that I will be working for starting in September, BASF. Little plug there. Right, but now let's talk about why. Why are catalysts in every industry? And going back to this concept of energy, right? Energy means money, and that's all that really matters in an industry. So if we look at this, let's take the example of some stack, right? If you've driven through a lot of industrial areas, have you ever really wondered what's actually coming out? What is that smoke or that steam? One common chemical that could be in that is ethylene, but of course there are very stringent guidelines of what can and cannot enter our atmosphere. Ethylene is certainly a big no-no. And so one of the ways we get around that is burning it. And so you introduce a very high temperature and you can actually get to just some water and carbon dioxide, right? There are strict limits on carbon dioxide as well, but again, that's much more favorable than just pure ethylene. The problem is that when you use this high temperature that's required to burn that, we also start interacting with the nitrogen that's in the air, and we get something much, much worse, and those are NOx compounds. So we can use a catalyst instead to lower that required energy, which not only saves us money, but something else very, very important happens here. We eliminate that undesired side product. And that goes back to the efficiency. And one of the biggest reasons research is focused on finding better catalysts, even for processes that already exist. There's always room for improvement. There's always a way to get rid of undesired side products, or in some way, just change that process altogether. And again, going even deeper, what does that mean? What does a catalyst actually look like? What are we working with? There's so many examples out there. Catalysts can honestly be just about anything. They can be in solution. They can be materials that help react with sunlight, or anything that can help shuttle electrons around and give us better batteries, or the metal organic frameworks that we heard Melissa talk about, or even just the atoms of a surface, which is where I can actually start talking about my research. I've spent 5 years trying to make plexiglass, just the very, very first step in that process, using ethylene gas and carbon monoxide gas. Plexiglass, hopefully a lot of you know, is a glass substitute. It is very widely used, so aquariums, bank glasses, anything that we want a stronger shatter-resistant substitute for glass. It is a polymer. A polymer is a material that is made up of small building units that have come together to form long chains. The polymerization, so the process of getting from one unit to many units, is very well established for this material. We're not really focused on that part. Instead, we are looking at how to actually create the monomer itself. How do we get to that building block in the first place? Currently, there is a route called the acetone cyanohydrin route. It's from the early 50s. I've done this work closely with Dow Chemical, and this is the route that they still use. They are the third largest producer of this monomer in the world. But there are a lot of problems with this current route. So even if we just start looking with acetone, right? We're thinking, okay, that's not so bad. But now we're taking large quantities of acetone, reacting it directly with large quantities of hydrogen cyanide. Not great. And then to that, we have to add copious amounts of concentrated sulfuric acid, and it just gets worse from there. Not to mention, this all requires high pressures, high temperatures. It's extremely dangerous for the workers, and as you can see, there's a lot of areas to make this process greener and more efficient. And really want to highlight, there's an incredible amount of waste generated here. There are some uses for that waste, such as fertilizer, but now you're talking about really expensive separations, and again, something we want to avoid. There are currently many processes out there that are slowly becoming industrially relevant. Again, BASF has a different route that does start with ethylene, which again is what I'm trying to do. But what's different from what I'm looking at to these is that these still have very significant limitations. First, they're very cost disadvantaged still, and they still require the use of a co-catalyst, so another material that is not consumed during that reaction, but that material is extremely corrosive. This is a huge problem when you're trying to design materials. So for example, if you had to think about your reactor, a $1 million reactor as a consumable part because you have an acid that just eats straight through it, that's a problem. Instead, I'm thinking, what other materials can I use? What catalysts out there can I use to achieve the same thing? I'm looking at metal sulfide materials to perform this reaction. Again, we see that ethylene and carbon monoxide gas, now just in the presence of water, much better than hydrogen cyanide, and getting to methyl methacrylate, that monomer, through a propanoic acid. This is just, again, an intermediate molecule, the very first step. That's all I've done. In 5 years, I've been able to look at this one step. But this can be done at lower pressures, lower temperatures, which makes it much safer and, again, most importantly, a little cheaper. And how? How do I do this? We take more or less what is a black powder. If you were to just look in my lab, you'd see a shelf of a variety of black powders. And at the surface of this, we have sulfur and various metal edges. And that's where that chemistry is occurring. But metal sulfides have been around for 100 years. What they're used for in industry isn't important here. What is that they are very well studied, but they have never once been looked at for this reaction. And that's huge. I take my gases, as well as that water, that catalyst, I put them in my reactors, and to give you an idea of scale, each reactor is about this big, a little less than about a softball. And I can seal that up, pressurize that with those gases, heat it up, and at the end, I'm left with a liquid product that I can detect using gas chromatography. And the first day in lab where I actually saw my desired product, I had a party. It was awesome. And that's what it actually looks like. That's as the experimentalist side, as opposed to some of the computational research we've heard today. And in the chemical engineering department, I was responsible for designing and building my own infrastructure that you see here. And that is 2 of those reactors that I showed. And all of this was, again, an effort to make that cheaper, greener plexiglass. Just a little detail here. One I'm most proud of is the design of this cooling system that you see that allowed me to rapidly heat up my reactors and cool them down. One of the biggest complaints you hear about experimental research is it's so slow, it's so inefficient. This allowed me to triple my productivity and run 4 reactions in a day instead of 1, maybe 2 if I was really ambitious that day. And I can all monitor and control that with a computer. So again, we're doing this in hopes to achieve that process that can actually be utilized in industry and replace the much more harmful, toxic version that exists currently, all towards a collaborative effort with my team here at Northwestern. We are a team of graduate students and postdocs. We're up on the Evanston campus, but working very closely with our mentors at Dow. They are very good at guiding us and telling us what is and isn't likely to be functional in an industrial setting. And with that, we can design our materials, test those, and use that again to inform different designs and go through that iterative process. So again, thank you so much for sticking through the end. I'd be happy to talk to anyone at the end of this. And I hope I showed you that we're getting close to cheaper, safer, greener plexiglass.